So today we'll be doing the 1995 Physics APC free response. The question reads, two stars A and B are in a circular orbit of radii RA and RB respectively about their common center of mass at point P, as shown above. Each star has the same period of revolution, T. So TA is equal to TB. Determine expressions for the following A, B, and C using the three quantities RA, RB, T, and fundamental concepts. So part A asks us for the centripetal acceleration of star A. We go to the fact that centripetal force is equal to ma, and centripetal force is mv squared divided by r equals mac. Since we want only the centripetal acceleration and these two masses are the same, we can cancel both of the m's out, and we're left with v squared over r equals centripetal acceleration. Now, the only problem here is we're not allowed to use a velocity, v. So using what we have, we can solve for v and plug it into the equation. We know that v is equal to distance over time, and the distance that's traveled by A is simply 2 pi RA, which is the circumference of the inner circle, divided by T, which is its period. Taking this information, we can plug it directly into this equation, and we get that centripetal acceleration is equal to, plug that in, we get 2 pi RA squared over T squared R. Okay. And I simply squared these because the velocity squared and plugged it back into the equation. All you need to do is simplify, and you will get that centripetal acceleration equals 4 pi squared over RA equals T squared. We canceled one of the r's with the r in the denominator. And so we have successfully completed part A. Part B asks us, determine the mass of star B. We can do this using centripetal force once again, exactly what we did here, except we're going to set it equal to the force of gravity. And so we know that centripetal force in this instance is equal to the force of gravity. The centripetal force is mv squared divided by r equals capital M little m g divided by r squared. And that is just an equation that we know. So first, let's solve for MB. So we need to put, distinguish these little m's. Are they MA or MB? We say that MA, 4 pi squared, RA divided by T squared, just plugging in prior information, is equal to G MB MA divided by RA plus RB squared. Sorry about that. In this case, we're making capital M MB and we're making little m MA. So we can cancel these MAs out because we're on both sides. And then this is the force of gravity between MB and MA. And using that property, we just solve it out and we get that MB is equal to 4 pi RA divided by GT squared, and we have to multiply that in, so it's RA plus RB squared. And that's our final equation. It might be difficult to see. Hold on. And that is the mass of B. So now we're looking for the mass of star A, and logically, if you just think about it, all we have to do is switch MB and MA. We find the centripetal force for MB, and that way we can cancel out the MBs on either side. And so when we make this MB, we have to make the radius RB, and then we just repeat the same steps, and we get to the same answer. Well, a different answer, but same exact process. So FC equals FG MV squared divided by R equals MG over R squared. Now, in this case, this M is going to be the mass of little b, this will be little b, and that will be A. In which case, this will be the radius of B, and once again, this is RA, RB squared. And logically, we just follow the same steps, and we get MA is equal to 4 pi RB, RA plus RB squared divided by GT squared. And essentially, all we did was replace the MAs and the MBs and switch the RAs with the RBs. Now, part D asks, the moment of inertia of the two-star system about its center of mass. So we're looking for I, the moment of inertia. And we know that I is always equal to the sum of mr squared. And in this case, the I total is going to be equal to the I of A plus the I of B. So we're simply adding up the two inertias. When we do that, we get that I total, and at this point we're just plugging it in. We know MARA squared plus MBRB squared, and that's the answer. It's that simple. Part E, which asks us to find the angular momentum of the system about the center of mass. This is slightly more challenging, but it's similar to moment of inertia. But for this we're using conservation. So L, we'll call it S, of the total system is going to equal the L of A plus the L of B. So we add up these two angular momentums, and we should get the total angular momentum. We know the basic way to find angular momentum is mvr. So we know that this is going to be equal to ma v a times ra plus m b v b r b. The only problem here, once again, is that we have velocity, and velocity is not one of the constants that we're allowed to use. So we plug in the velocity that we found before, and we get that Ls is equal to ma, velocity distance over time, so we know that's 2 pi ra over t, right, multiplied by ra plus mb, velocity once again is 2 pi r, b though, because it's the second orbit, divided by t over r, b. So we just plugged in 2 pi r over t for velocity, and we solve it all out, and just go up here where there's space, we get that total angular momentum is equal to 2 pi t, taking out that from the equation, is equal to MARA squared plus MBRB squared. We're squaring because we just multiplied out those two RBs. And that is it for this free response.